it's fine.
Okay, so it's a great pleasure to have Olalla Castro-Alvaredo to this set of lectures on entanglement in quantum field theory, an introduction to branch point with field and their application. Olalla is one of the pioneer and the expert on the field, so it's really a great pleasure to have her here. Please, Olalla, start your lecture.
Okay, thank you very much. So it's a great pleasure to be here and to welcome you into my home in North London. So it would have been nice to be in Florence, but okay, this is not too bad. So yeah, you have seen the title of my lecture. So this is about entanglement and about a particular technique, computer entanglement. So before I go into the lecture itself, for which I'm going to use slides, I'm going to tell you a few basic things about how I'm going to do this course. So some generic information. And the first thing is about getting in touch. So of course you have opportunity to ask questions in the lectures and in the discussion sessions. But if something comes to your mind after you forgot to ask or you were too shy to ask, you can always email me. I'm happy to answer any questions you might have. I have actually put all the lecture notes that I'm going to use over the next 3 days together with some exercises in a website that I created for this course, specifically for this course. So if you go to this address, which is also going to appear on my slides later, you will find all the material. So you can also decide in advance if you find it useful to come. I hope you will. I have put some exercises there and the solutions as well. So hopefully you can first try them without looking at solutions if you can. I think that would be a bit more interesting for you, but if you get stuck, there are solutions there as well. Something about references. So when I do my presentations, I tend to present references in these forms. I just write the authors and then the year. So I don't write the journal, all the details, just to make things a bit shorter. I understand that for graduate course, this is maybe not the best approach, but most of the time that is enough information to figure out what the paper is. But if you ever have any questions, you can write to me or ask me, and I can give you the full reference. And the final thing is just to say that this is a 6-hour course, so it's not going to be completely detailed about everything, and I will assume a certain background knowledge of integrability and CFT. It's not a rigorous course in a mathematical sense, but what I hope is that you would get enough ideas and enough intuition by the end of it to understand what these branch point twist fields are and how they can be used in this context. And this is my objective. So with this, I'm going to get out of this screen of this presentation because this was just this one slide. So I'm gonna share the first part of the lectures with you. Okay, so just one moment. So share my screen, go on full screen, and then I have to share again because I think it has now disappeared. So just a minute. Okay, so hopefully you can all see my presentation now. So I have given them numbers just to indicate kind of the first hour, second hour, and so on. So let's see how it goes. So, so let me start. So the first part is about entanglement measures in QFT. So I'm going to talk about twist fields, but twist fields have one main application, which is to the computation of entanglement measures. And so I thought it would be good to have at least 1 hour or one part of this lecture, this course, talking about entanglement measures, at least the most popular ones, and how you define them. So let me start from the beginning somehow. So talking about entanglement. So I think all of you know that, well, one way to think about entanglement is that if you have a state of quantum system that is entangled, it means that performing a localized measurement in a space and time may instantaneously affect local measurements far away. So this is the famous spooky action at a distance of Einstein. So I think you will also be familiar with this kind of example. So this is one of the Bell states. And this is the typical state which we normally understand as having a lot of entanglement. In fact, a maximum amount of entanglement between these two spins. Okay, you can think of these two variables as two spins. And the reason why it has maximum entanglement is that essentially if you look at one of the parts of the state, if you know the state of one spin, whether it's up or down, you immediately know everything about the other spin. So it gives you full information. If you want to compute averages of observables in the system, you can use that state and just sandwich the observable there. So that is an example of a state where, which is entangled for two spins. And well, what is special about this, according to Bell's inequality, is that this cannot be described by local variables. So it's really a quantum phenomenon, entanglement, a real quantum phenomenon. If you want to compare this to something different, then you could think of a state that is looks similar in some sense. So it contains also these combinations of spins up and down, but it actually contains all possible combinations, which actually means this state is factorizable. So you can factorize it into the product of degrees of freedom of one spin, degrees of freedom of the other spin. And in this case, this state is actually not entangled at all, because knowing something about one spin tells you nothing about the other. Now, all of this is very simple. You all have learned this in quantum mechanics many years ago. But where this gets a bit more complicated is if you have many of these spins, in which case you have what we sometimes call a many-body quantum system, or a quantum spin chain of the type you would have been seeing with my colleague Bolash in his Betances lectures, I'm sure. So what do you do in that case? So what happens if you have a many-body quantum system? So here is a picture I got from the internet, a nice illustration. Well, what happens at some level is the same, it's quite similar. So first of all, you can try and, you could try and think of entanglement in a similar way. So think of your system, of your state as divided in two parts. Now, in the previous examples, the two parts were very clear. It was just two spins. So one spin in each part. If you have many spins, you can still do a division in two parts. This is called a bipartition. And this is why we often talk about bipartite entanglement. This is not the only thing you could do, but it turns out that most of the popular measures of entanglement, they are designed for bipartite systems, because these are the situations in which it is easiest to come up with good measures. It is not the only situation, but it's the only one I will talk about. So if I divided that state into two parts, into two sets of spins, I can again have two situations. I can have a situation where the two parts of the state completely factorized. And so in the left-hand side picture, if I forgot about subsystem B in some way, the part of the state corresponding to system A is still a pure state. But if I look at the picture on the right-hand side, and I think of entanglement as all these little links joining all these dots, all those spins, so somehow all these spins are kind of talking to each other, entangled to each other, then my state is not factorized anymore. And that means that if somehow I could, by some method, forget about the existence of subsystem B, let's say, what would be left for A would not be a pure state anymore. It would be a mixed state of some kind. And that mixing will arise purely from the fact that I'm forgetting the environment. I'm forgetting about subsystem B. Now, when I say forgetting, what it means in practice, in mathematical terms later on, is that you trace out the degrees of freedom of B. And we're going to see that in the definitions in the next slide. So we can ask then, what provides a good measure of entanglement? Now, this paper that I mentioned here is a review I found a few years ago, which I find quite nice, because they have a list of many measures of entanglement, and there are lots, and they describe their mathematical properties in quite some detail. And there are many different properties that you can have, but if you look at them, you tend to find that there are some common properties that people want to have for any measure of entanglement, or almost any. And one that you find very often, including in this paper, is something called, is something like this. It should be an entanglement monotone. There should be no increase under local operations and classical communications. So this is the type of language that you encounter in information theory, which is an area I actually don't know that much about. And when people talk about that in information theory, usually they are thinking about the sort of Alice and Bob problems you might have read about in the literature. So you think about Alice and Bob, each of them owning some qubit, let's say, and doing some operation on their qubit, a local operation, and then talking to each other on the phone. That is a classical communication. So this is the kind of setups they are thinking about. And to be honest, I find it a bit difficult to think how this applies to the sort of problems we're dealing with in here. But I think the thing that makes sense, at least, is to talk about monotonicity, entanglement monotone. So roughly, that is the idea that if the measure is any good, it should get bigger as a number, the more entanglement there is in the system. Okay, so there is a sense of growth for this quantity. It should also be invariant under unitary transformations. That is quite a natural requirement. And we would like this measure to be zero for separable states, factorizable states, like the state on the left-hand side in my picture. So I would like to be able to show that any of these functions gives me a zero when I compute entanglement of A with respect to B in that situation. And then there is one final property, which is a little bit the contrary of this, or the opposite, which is that it should be non-zero for non-separable states. Now, I wrote usually in there because a few years ago, actually, I was quite embarrassed. I was giving a talk similar to this, and I didn't have the usually there. I just said non-zero for non-separable states. And then I went on to talk about several measures, including one that is called the logarithmic negativity. And somebody in the audience told me, well, actually, the logarithmic negativity can be zero for non-separable states. And I actually didn't know this, so I now have written usually. And I understand now that in the context of information theory, people often or sometimes distinguish between different types of entanglement. And sometimes they call it distillable and non-distillable entanglement. So in a way, not all entanglement is made the same. Some entanglement is kind of useful, can be extracted, and some is not. And again, this is an area I don't know so much about. So let's see that usually we would like these measures to be non-zero if the states are non-separable. I believe this is true for entanglement entropy. So since I mentioned it, so let's mention these measures, the measures I'm going to be telling you about today. So the most popular and the most famous is the bipartite entanglement entropy. Sometimes I call it just entanglement entropy. Sometimes I call it bipartite entanglement entropy. Sometimes I call it von Neumann entanglement entropy. They are all equivalent, these names, and people use all of them. There's also a family of entropies labeled by an index, which are called the Renyi entropies. They are also very popular measures of entanglement. And then there is a quite different measure, which is called the logarithmic negativity. And these are all good according to these properties here. Okay. So now that I have given you a few names and a few ideas about this, let me give you a slightly more precise definition of all these things. So the context in which it is easiest to think about measures of entanglement actually is the context of discrete systems, quantum spin chains, just because of the examples I gave you with the spins and how, if you think of spins, these are local degrees of freedom and they can be easily identified as such. When you go to quantum field theory, that is a little bit less clear, let's say. And that's why I'm going to start talking about quantum spin chain. And then immediately in the next slide, I'm going to be talking about quantum field theory. So there's going to be a quite abrupt change from one thing to the other. So I'm going to have to assume that at least you understand roughly that how you go from one to the other. The idea that if you have a spin chain, you zoom out, you do a so-called scaling limit, then you get an effective description of that theory, which is what we call a quantum field theory. So unfortunately, I don't have time to explain in detail how you go from one to the other, but they are connected. And hopefully you will see that also through some numerical results I'll show you later. So for now, let's start with a spin chain. So this is a spin chain with many body quantum system, many spins. And we're going to think of bipartition where the subsystem A are the red spins and subsystem B is the rest. And let's imagine this is very long and we have periodic boundary conditions. So the blue dots, they meet again, okay? Eventually in QFT, we will make this system infinite. So it doesn't really matter very much, the boundaries at the moment. So this is our bipartition. So if we have this situation, the entanglement entropy is defined in this way. So suppose that we find an eigenstate of this chain. So phi is the pure state of this system. We are at zero temperature. So we have, no temperature here. We have pure state, and then we take the product with its conjugate, and we trace over the degrees of freedom of the complementary of A. So the blue dots, this is A bar. We trace, so we forget about the blue dots. We trace out these degrees of freedom. the result of that is a matrix, which is called the reduced density matrix of subsystem A, row A. And if we now take this matrix and plug it into this formula on the left, we get the von Neumann entanglement entropy. Okay, and if you're a little bit familiar with classical information theory, that looks exactly like the Shannon entropy. It's the quantum generalization of that. So row A log of row A. Okay, so this is a simple definition. That's all it is. And then there are other entropies I mentioned earlier. So let me mention some of them here. So the Renyi entropies I mentioned, these are quite important. They're going to come up quite a lot in this course. And they're defined in this way. So you see that this row A again appears here in a trace, but it is a trace of row A to the power of n, when n is some real number for now. And there are other entropies like Sally's entropies, entropy defined in terms of that same quantity. Okay. Now these two entropies, both Renyi and Sally's, they depend on this one parameter. So it's a one parameter family. And they both have the property that if you send n to 1, so you do the limit n to 1, you get the von Neumann entropy. So you can compute Renyi entropies. If you know all the Renyi entropies, you also know the von Neumann entropy. You can compute it. Okay, you can go from one to the other. Okay, so so these are the main definitions for now. I will talk about the negativity a little bit later. So in the next slide, I have something which I'm going to try to do with you so that there is a little bit more of audience participation. So I'm going to be doing some polls, but unfortunately I haven't been able to use the poll option on Zoom. And so I'm going to be doing these polls a little bit in the kind of brute force way. And I'm going to explain to you how. So first of all, I'm going to show you a question. This is my first poll. So I want to find out how many of you think, if you think any of these quantities is experimentally measurable. Okay, so are these measures of entanglement something one can measure in the lab? So think about it. There are two options, yes or no. And now listen attentively to me. So if you think the answer is yes, okay, the first one, I want all the people that think the answer is yes to write something on the chat right now, but only those that think it's a yes. So hopefully when you do that, I should see a number appearing on the chat. I should indicate how many people have chosen that. Okay, so if you think it's yes, write something on the chat right now. Sorry. What happened here? Okay, I'm getting 7 votes. Okay, keep them coming. 8, 9, 10, 11, 12, 13, 14, 16, 17, 17, 18. Okay, so a lot of people, I mean, it seems to me, think that these quantities are measurable, at least some of them. I assume all of these votes are for yes. Okay, so I think they stop now. So 22, I can see 22 people have seem to have voted for yes. Okay, which is a bit less than half. Okay, so more people, I assume more people think this is not measurable. So when I started working in this field, I used to get this comment quite a lot. People will come to me and say, oh, what's the point of computing anything? You cannot measure this stuff. This is not measurable. And I think it was true at the time, although, I mean, this is not the reason why I was working in this field, because I'm never going to do experiments. And I'll hopefully convince you later that there are other reasons why these quantities are interesting. But it turns out that in recent times, they have become measurable, at least some of them. So if you're interested in this, I just went online yesterday and had a look. And for example, there is some paper from 2018 from the group of Peter Söhle in Innsbruck, where they talk about measuring the second Renyi entropy. So that would be the Renyi entropy here, which has index n equals 2. I think this seems to be the most popular thing that people can measure, perhaps the only one. I'm not an expert, but I think there are several experiments on this. So it seems some of these quantities can even be measured experimentally now, okay? So the answer would have been yes, okay? So you were in a minority, but you were right. Okay, so I think these polls kind of work like this. So this is how, there's gonna be quite a few questions like that as we go along. And now you know what you have to do. So people on the first choice vote first, and so on. Okay, so I hope you find this entertaining, just to break the flow a little bit. Okay, so now we're going to go to the next page, and we are actually going to experience a big jump, in terms of content, in a sense, because until now I was talking about quantum spin chains, and now suddenly I'm going to be talking about quantum field theory. So it is intellectually quite a jump. So imagine you now took the scaling limit of this quantum spin chain, and you now have a quantum field theory description of the situation. And in this context, we want to find an interpretation for this trace of rho, and in particular for this trace of rho to the n. It turns out that this interpretation is going to be eventually what allows us to do computations, especially when we go beyond conformal field theory. So this is a part of our interpretation, which is not very, very rigorous, but hopefully will give you an idea what is happening. So this object, trace of rho to the n, remember, this appears in the Renyi entropies. It appears in the Salis entropy. And if you take limit n to 1, it also kind of gives you von Neumann entropy. So it's kind of an important building block. So what is this trace of rho to the n? So trace of rho is a partition function in the usual interpretation in QFT. So you have to remember there was this product of state with conjugate, state of the system. So that is a partition function of the system, but with a twist in a sense, because you have traced out the degrees of freedom of the subsystem, the complementary of A. Now you want to do that trace. So what does it mean doing the trace on this rho? So rho is a matrix, but it is in QFT, this is the entries of this matrix would be functions of space-time, x and t, and would be functions of the states of the system. And in fact, computing trace of rho to the n, one way to think about that is to think about this product that I've written here. So the power n is the fact that we have n of these matrix elements, if you wish. And each of these matrix elements is between two states, state 5, psi 1, psi 2. And these states are connected to each other because this is a product. And the first one and the last one are identical because this is a trace. This is what, so they close because of the trace. The sum of states here is a simplification to mean that we are summing over all this psi 1, psi n, and phi. Now this, I tell you, has an interpretation as a partition function. And it is a partition function Zn and properly normalized. So we're going to normalize by Z1 to the n, just purely to make sure that when n goes to 1, this becomes 1. Okay, it becomes trivial. So it turns out this has an interpretation as a partition function on a Riemann surface with n sheets. And where does this come from? Well, it comes from the idea that you can think of these individual matrix elements as objects that live in a space-time that looks like this sheet, this complex plane. So we have this complex plane, and in this complex plane, we have a slit. And on each side of the slit, we have these different states. And we only have this slit in the region corresponding to subsystem A, which now in the quantum field theory has a certain spatial length L, okay? Like in the spin chain, it had a certain length. This only is there for A because for subsystem, for the rest, so the complement of A, we have already zipped it in a way, okay? We traced over those degrees of freedom, so they're not there anymore. The only thing that is open is that slit in there. Now, if you accept that interpretation, then the trace of rho to the n immediately acquires a geometrical, well, can be associated with a geometric picture, which is the picture of stacking many of these sheets on top of each other. And if you stack many of these sheets on top of each other and connect them according to the connection of these states in here, what you get is a structure that looks like this. So you get a Riemann surface, which has n sheets, and these n sheets are cyclically connected, with the last one connected to the first one, and the two sides of the branch cut connected, connected to the sheet immediately above and immediately below, okay? So you get that structure appearing as a consequence of this power n in the trace. Now, because this trace, we are saying we interpret it as a partition function, another way to write it in quantum field theory, a little bit more formally, is something like this. So we have our Lagrangian of our theory on this manifold, and we have a measure on this manifold, which means essentially that there are, this measure includes the connection conditions between the branch cuts on these different Riemann sheets, okay? Now, the interesting thing is that this trace of rho to the n is a partition function, but it is a partition function on a replica theory, hence the title of this slide, replication. So what does this mean? Well, in order for this theory to have this symmetry, this replica symmetry, we are gonna, this Lagrangian that we're writing here is not exactly the Lagrangian of the original QFT. It is actually the Lagrangian associated with n non-interacting copies of this original QFT. So we are replicating our theory, we are doing n copies of it. And after replicating, what we end up is with this result, that the trace of this rho to the n for that theory, for that replica theory, is a partition function on this geometry, on this Riemann surface, on this Riemann sheet. So, so we have a complicated Riemann surface, well, not so complicated, with a branch cut in there and two branch points. So just to well, discuss this a little bit more, something a bit about this Riemann surface, let me ask you one more question on the poll then. So what kind of function becomes single value on this Riemann surface? So in other words, what is this the Riemann surface of in complex analysis? Okay, so when you study complex analysis, you study functions of complex variables. And well, sometimes if they are not single valued, you have a Riemann surface associated to them. So what would be the function which has this Riemann surface I just showed you? So I'm giving you two options. If you think it is A, I'll ask you to vote. And I'll assume everybody else thinks it's B. Okay, so anybody thinks it's A. Okay, I see no votes coming. So, okay, so maybe that was a little bit too obvious, that option A. It was a bit naughty of me. So option A is not true, of course, and hopefully that's what you all felt, that it didn't make sense. No, it doesn't make sense. It's not a log. The Riemann surface of a logarithm has infinitely many Riemann sheets, in fact. So this Riemann surface is actually the Riemann surface associated to the nth root of a function. And in fact, because you have two branch points, it's an nth root of the ratio of two functions like this. And x1 and x2 would be the two branch points on the Riemann surface. Okay. Now this function plays a certain role, because when you do computations in conformal field theory, this is going to become precisely the conformal map that you need to go from this Riemann surface to the complex, back to the complex plane. So this is useful to know for later, and for some of the problems I suggested, this will be useful. Okay, so we have now kind of migrated to quantum field theory, and we have given this trace of rho to the n a nice interpretation. Because this nice interpretation exists, that is one of the reasons why, especially with the technique I'm going to talk about, most of the time we are computing Renyi entropies rather than von Neumann entropies, because trace of rho to the n is the natural object in this context. So with this picture, then there are other issues that arise. So as I told you, you can take the limit n to 1 of the Renyi entropies to get von Neumann. Or if you wish, when you do that limit, actually in effect, what you have to do is this derivative. And this result is something that sometimes is called the replica trick. Okay, again, replica appears here. Okay, so there's that relation. But for what I have been telling you now, so this picture, which is related to the Riemann surface, if you believe that picture, then this n, this index n, needs to be an integer larger than 1, hopefully. So it cannot be any real number anymore in this picture. I think there is a question in the chat. Why this is easier? Why this an easier way to calculate the case of n equals 1? Oh, yes. Why is it easier? So it is not always easier, but it's going to be easier because the method that I'm going to talk about later, so branch point twist fields specifically, it is a method that allows you to compute this trace of rho to the n. Okay, so this is what the method naturally gives you. And so because that comes directly from the method, at least for an integer, this is the quantity that we compute most of the time in quantum field theory. Now, if you're doing other methods, sometimes it's as easy to compute one thing or the other. In fact, there will be a question about that a little later, but that's a good question, okay? So that is, my comment was more specific about the method I'm going to explain, which is for trace of rho to the n. So if we want to do the limit going of n going to 1, if we want to be able to compute that limit, we need to be able to compute these Renyi entropies also for values of n that are not integer. And if we believe this Riemann surface picture, then this is not so natural. It's a little bit difficult to imagine how you make sense of an n that is a real number rather than an integer number. So that is a problem, okay? We need to have to extend somehow our notion of replica to n bigger than 1 and real. And this is an analytic continuation problem. So when we do calculations, again, with twist fields, for example, we're gonna get results for an integer. And if we want to go from there to von Neumann, we're gonna have to develop some way to analytically continue those results to values of n that are non-integer. And this is not a problem that is generically understood, at least not in quantum field theory. It is a difficult problem, and it is solved in some cases, but not in others. So, so this is, well, something to deal with, okay? But I'm not really gonna talk a lot about that, except in my third day of lectures, where I will give an example where this plays a role. So for this reason also, it's often easier, as I just said, to compute Renyi entropies with an integer. So we don't have to worry about all of that. Now, relating to the question that I was asked, in fact, I have another question for you now. Would like to know what you think about this. So does this mean that it is numerically harder to compute the von Neumann entropy than the Renyi entropies? So what do you think about that? So if you think it is no harder, I would like you to write something on the chat. So those that think no, write something now. And those that think yes, don't do anything. Okay, so there's quite a few no's that are coming through. $18, okay, 20, 21, 2, 3, okay. Okay, so I think we can probably stop in there. So about half the people here think it is no harder to compute one than the other. So it's kind of half-half, which is interesting. So the answer that I had in mind is that it was no, it was not harder. But actually, I mean, there may be situations where that's not true. So the way I was thinking about this question is that the problem of the analytic continuation is an analytic problem. It's a problem that you have when you have an analytic formula for an integer. But when you do numerics, most of the time, what you do is you compute this reduced density matrix and you compute its eigenvalues. And once you know the eigenvalues, then you can compute any Renyi entropy, any measure you like. You can just raise these eigenvalues to any power you like. It could be an integer or not. So from a numerical point of view, in general, there should be no reason why it is harder to compute Renyi entropies with non-integer indices. It is the same. So, the answer I had in mind was a no. Okay, so this analytic continuation problem is a mathematical problem, not necessarily a numerical problem. Okay, so let's continue then. So what else? So I've told you a little bit about entanglement entropy and how you can define it. I'm going to tell you about another measure now. This is called the logarithmic negativity. And this is also a good measure of entanglement according to those properties I mentioned at the beginning. But it is a good measure both in pure and in mixed states and for non-complementary regions such as AB in this picture. Okay, so again, I'm going to start with a spin chain because it's an easier environment to imagine all these local regions, local bunches of spins. But in the case of the negativity, we need essentially three regions, A, B, and C. And what we are asking is about entanglement of A with respect to B, given that C also exists. So A and B are now non-complementary regions, namely their union doesn't make the whole system. Now, this negativity or logarithmic negativity has been studied by lots of people, especially in the context of quantum information, and also more recently in our area. So in the context of conformal field theory, Pasquale in particular has done a lot of work, and also we did a little bit in QFT and many other people. So how is this defined? So there is a definition of this measure, which also is also based on reduced density matrices. In fact, all these measures are based in a way or another on reduced density matrices. And the way this is usually written is this. So there is a reduced density matrix again, but now this is the reduced density matrix of the union of A and B, okay? And that means we have to trace away the degrees of freedom of this region C, okay? And suppose we are in a pure state for now. I know that in my definition, I said you could have mixed states, and that's fine, but we'll focus on pure states. They are complicated enough. So once you define this reduced density matrix, you plug it into this formula on the left, and this is the logarithmic negativity. So it has a logarithm, hence the logarithmic. And then you have a trace as before, and then you have this sort of modulus symbol there, and you have this TB symbol there. So what is that? So there are two operations here. The first thing is this modulus, or this thing that looks like a modulus. It is actually, I mean, what we have inside is a matrix, so it's not a modulus. It is something called the trace norm. And what the trace norm does is that it gives you, I mean, when you compute this trace, what you get is the sum, it's not the sum of the eigenvalues of this matrix, but rather the sum of the absolute values of the eigenvalues of this matrix. So the trace norm is the operation that puts an absolute value on the eigenvalues of this matrix. Now, why do we have to do this? Or why do we do this here? Well, we do this here because this matrix, rho, this reduced density matrix with this TB on top, is the original reduced density matrix, where we have performed some additional operation. And this additional operation is called the partial transposition in subsystem B. So what that means, in essence, is that if we have our reduced density matrix and we have some matrix elements of it, which will include vectors in subsystems A and B, we transpose with respect to subsystem B only, okay? The resulting matrix elements that we get will correspond to some other matrix. And this is the partially transposed reduced density matrix. Now, when you do this partial transposition operation, which by the way is basis independent, apparently this has been proven, when you do this operation, the matrix that you get is not necessarily positive definite anymore. So these reduced density matrices normally, in unitary theories at least, should be positive definite. So the eigenvalues would be positive. But after you do this partial transposition, the eigenvalues are not necessarily positive. And that's why somehow putting the absolute value removes that problem, okay? So makes everything possible, positive. So the fact that you, want to make some positive things only, that's where the name sort of negativity comes from. So you take away all the negativity of these eigenvalues. Now, I know that this definition is not, I haven't motivated it at all. I can just tell you that people have worked for many years on investigating this definition and coming to the conclusion that such a function has all the suitable properties to become a good measure of entanglement. Okay, so that's all I would say to justify it. So you see that it's also based on a reduced density matrix. Now, one nice thing about this logarithmic negativity is that there is also a way to generalize this definition so that you can play with this idea of replicas. And this is a very beautiful idea that actually is due to Pasquale, Cardi, and Tony from a few years ago. And what they realized is that you could instead, okay, there's a little typo here in my bracket, you could instead compute something like this. I call this a replica logarithmic negativity. So you could compute something very similar where instead of having a trace norm, you just have the power n of this partially transposed density matrix. Okay, so you have the power n, and then if you want to compute the logarithmic negativity, what you have to do is to analytically continue this to n1 from n even. So this is what I wanted to write here, and I made a little typo. So what does this mean? Well, it means that when we compute these powers of rho to the n, take the trace and then the log, we want to compute lots of those, but we want to compute them only for n even. Okay, so suppose we compute them for 2, for 4, for 6, for 8. We find the function for n even, and then we analytically continue that function to n equals 1. It seems a slightly weird thing to do, but that's what you need to do, because only by having even powers, you get rid of the negative signs of the eigenvalues of these metrics. Okay, so this is the analytic continuation that you have to do. Okay, and that's what this NE here means, is the n even. Okay, so this is a picture that that was proposed, and which is also very useful, because then it allows us to use again these ideas of the replica quantum field theory to do calculations, also for the negativity. Okay, so there is also a partition function picture in this case, and if you think about the spin chain picture that we had here with these 3 regions A, B, and C, I think it's not too complicated to imagine what the partition function is going to look like. So you're going to have also n sheets again. And now there are 2 branch cuts instead of just 1, which are the regions A and B, okay, since we trace over C only. And this is a picture actually from that paper, Calabrese, Cardi, and Tony. And this picture, if you look closely, it shows you that the connectivity of these branch cuts is different for each of them. So they are connected cyclically, but in the opposite way. And that's what it means. That's because of this partial transposition on region B only. So that changes the kind of orientation of the connections. And this picture looks a little bit like, I think I'm not the first one to notice this, but this looks a little bit like the escalators on the London Tube. And this is actually, I think, a picture of the tube I used to take when I was going to the office, which was actually the last time I went was about a year ago because of COVID. It's actually the deepest tube station in London, Angel. So it has a very long escalator. So it looks a little bit like this Riemann surface. Okay, so by the way, don't feel shy to ask questions. I would be happy if you do that, especially in the chat. I mean, because if you talk, usually when I go into my flow, if you suddenly start talking, I'll get really startled, I think. But do write things on the chat if you have questions. Okay, so what else? So what motivations do we have to study entanglement? Well, there are very many, really. I mean, for one, mathematically, it's very interesting to study these functions and to study their properties, and some people do just that. But in the context of integral quantum field theory, conformal field theory, one motivation, one reason is that entanglement growth is a key indicator of how effectively a quantum system can be simulated on a computer. So knowing about entanglement entropy, for example, tells us something about how well we can do this. Okay, and this is one of the actually original big motivators for people to look at this in the context of spin chains and conformal field theory. Something that is very interesting about entanglement measures that we will discuss a bit more now is that they have remarkably universal features, okay? And in a moment, I'm gonna ask you a little bit more closely about what that means. But I think some of you would have some idea already what this means. So a prime example, for example, is what happens in conformal field theories in the situation I described at the beginning of this talk. So when you have 2 complementary systems and the subsystem A is made of a single block, so a single interval entanglement. So if you look at that situation, which people did in many papers, or if you look at the logarithmic negativity as well, you find some results which contain at least some part which is very universal. So if you look at the entropy of one interval in conformal field theory, which is the formula on the left, you see that there is a constant in front of this logarithm, which is C, and this C is the conformal, is the central charge of the conformal field theory. So quantity that characterize a whole set of conformal field theories associated to the same critical, a whole lot of theories which have the same critical point, the same C. And if you compute the logarithmic negativity of so-called adjacent regions, which just means that A and B, instead of having a little region in between them, that little region is reduced to 0 between A and B, so A and B are adjacent. In that case, the negativity has a quite simple form in CFT that was found also in the same paper I mentioned earlier. And that function also has a coefficient in front, which is the central charge of CFT. So this is an example of this universality, that somehow if you wanted, for example, if you were simulating some quantum system on the computer, and you wanted to find out whether this system is critical or not, or what its critical point is, if you computed the entropy, you could immediately extract the central charge associated to that critical point. Now, here there is a parameter I use in all my formulas. I like to write them in this way. This epsilon is just some length measure. I mean, in a spin chain, you could think of that as the spacing between the spins, for example. And this is a non-universal short distance cutoff. So this is a quantity that is not necessarily universal. It depends on the lattice spacing, for example. Okay, so it's a constant. C is the central charge. So, okay, that's an example of universality. So both the entanglement entropy and the logarithmic negativity display universal behavior and also dependence on universal features of CFT. Other ways in which entanglement measures are interesting, which are perhaps of interest more recently, are, for example, the study of the dynamics of entanglement. So in recent times, people have been very interested in looking at quantum field theory in one dimension and in a situation that is out of equilibrium. Okay, so after what people call a quantum quench. And it turns out that if you have a system out of equilibrium that is evolving in time, the way the entanglement evolves in time can tell us a lot about what's happening in that system out of equilibrium. So again, it encapsulates some quite universal fundamental properties about the system. So since this word universal is very popular in this context, I would like to ask you to think a little bit more about what it means when we say something is universal, because actually very often we mean sometimes different things by the same word. So I want to give you three options. So something is universal when it's the same for a whole bunch of theories, or it does not depend on renormalization constants, or we just say because it sounds cool, which is also a good reason that I like. So if you think it's A, I'd like you to write something now. Okay, so A is quite popular. It seems to be always 24. Ah, no, 25. Okay, 27. Okay, very nice. 27 for A. Okay, so stop there, the A's. So who thinks it could be B? I'm going to clear this. Anyone thinks it could be B? Okay, I can see one vote for B only. Maybe I missed some, I don't know. 2. Okay. And well, the rest, I assume they think is C, which is quite a few. Okay, there are 4 for B. 5, okay, 6. Okay, so the B's are a little bit shy, I'm not so sure. Okay, so, well, I think we can stop there. So a lot of people think A is a good answer, and actually, yes, it's a good answer. And in a way, it's what I said before when I was talking about conformal field theory in the previous slide. I was saying, well, the entanglement captures universal features because it depends on the central charge, and the central charge is something that is common to a whole bunch of theories that have the same underlying critical point. So that covers A, but actually, in a sense, well, all of them are correct. So, okay, to just say because it sounds cool was a bit cheeky, but B is also correct. And you will see an example of that later on when we come to results in away from the criticality, so in massive quantum field theory. So sometimes when we say something is universal, actually in quantum field theory more generally, we mean that something does not depend on the microscopic details of the theory. Okay, so encapsulates some information about the theory that is quite fundamental, that doesn't depend on details, okay? And for example, depending just on C, okay? But in quantum field theory, sometimes we will have results that I will claim are universal, even though they are for particular theory only, just because they don't depend on renormalization scheme. So they don't depend on how you do the calculation, you will always get the same number. And I will also say that this is universal, although it's a little bit differently universal from getting central charge, for example. So this is just to make you aware that sometimes we use the word universal, meaning slightly different things. Okay, thanks for answering. Okay, I hope you're finding this interesting. Okay, so let me then summarize a few famous results and some slightly less famous results for all these quantities. Okay, so without telling you where they come from, and then in the next part of the lecture, I'll tell you how you can compute at least some of them using these twist fields. So if you look at results for conformal field theory, which I will think of as short distance limits. So we may not be exactly on a criticality on a conformal field theory, but if we look at the entanglement of an interval, and that interval is much smaller than the correlation length, which is my psi in there, then even if my system is not globally critical, at the level of that interval, the interval will feel as if it was critical because L is a lot smaller than the correlation length. So we will be in the CFT regime in that case. And in that case, there are some very famous results, including the one I showed you earlier for the von Neumann entropy. So more generally, for the Renyi entropies, we have a result that looks like this. So again, I have this non-universal parameter that I always write here, this epsilon. So L over epsilon is a-dimensional. We have the central charge, so that's still there. But when we compute Renyi entropies, we also have a dependence on this parameter n. And of course, you see that when you send n to 1, you get the C over 6 in there. And then there is also this other quantity here, which is boundary of A. So this boundary of A, this is the number of boundary points. So if you're looking at a finite interval of length L, there are 2 boundary points. So that partial A there, this boundary of A, number of boundary points will be 2 in that case. And so if you put that equals 2, n equals 1, you get the C over 3 of my previous formula. So this is the formula for Renyi entropy in CFT. What happens if you are in massive QFT instead? So you have a gapped system, or in other words, you have a subsystem of a length that is much bigger than the correlation length of your system. In that case, you're in what I would call a massive regime, quantum field theory. And what the entropy does in that case is a bit different. What it does is to saturate. It saturates to a constant, okay? And by the way, I forgot to put a reference there, but this is a result that was actually proven mathematically even by Hastings. Let me check, there is a question on the chat. Is this true of any spatial dimensionality? No, I don't think so. So we are always talking about, well, I don't know if you mean it in that sense, but we're always talking about one-dimensional theories. So one dimension in a space. So this L really is a length in here. Okay, so this is all I'm talking about at the moment. Some other comment? Yeah, no problem, thanks. Thanks for asking. Okay, so so if we are in a gapped situation, what the entropy does is to saturate. So this is intuitively not so hard to understand. So the idea is that if you think about your regions A and B, entanglement between these regions, you can think of it almost as some links connecting one region to the other. And essentially the correlation length tells you how far these links can go. So if you have a region of a certain length that is quite large compared to correlation length, eventually you're gonna get, I mean, if you make the length very large, eventually you're gonna get as many links as you could possibly have, and then you cannot have any more. So entanglement saturates to a constant. Now, the way I wrote it here, it doesn't look like it because it looks complicated. It doesn't look like a constant, it looks like a function. But what I mean by constant is that this does not depend on the length of the system, except for the corrections. But if you forget about these order exponential corrections, all of the rest have no L in it. So in that sense, they are constants. They depend on n, of course, because these are the Renyi entropies. They depend on the correlation length, which is the inverse of this mass scale M1 here. This is defined a bit later. So you can think of the mass as the inverse correlation length. And it depends again on the number of boundary points. That's also there. And some constant UN. Okay. But all of this, although it looks like sort of complicated, in the end, it's just a number. It's just a constant depending on the correlation length. Okay, so for fixed correlation length, this is fixed. If you take the limit n to 1 of this formula, then that constant becomes another constant, which is the first two terms in my formula here. And these exponential corrections, you can actually compute them precisely. And it turns out they take a very simple form, this form here with a Bessel function. Okay, so this is a result that we actually got a few years ago in this paper. So there are corrections to saturation that you can compute in quantum field theory. They depend on the masses of the particles in the spectrum, because now we are in the massive regime, but they depend in a very universal way. Let me use the word. So in a way that is the same for all quantum field theories, in one dimension at least. So that is very nice. Okay, so we have corrections to saturation which are universally of this form. And let me say as well that this U1 is also universal in the sense that for each quantum field theory, you can compute this U and it is a precise number which doesn't depend on non-universal constants. Okay, so it is going to depend actually, just to anticipate, on the expectation value of that famous twist field of this course, okay, which is still to come up. So these are some known results, both at the criticality and away from criticality. So I'm going to give you another quiz just to tease you a little bit. So this one is about something that people talk about a lot, the area law. So this is something you probably heard about in some seminar, at least. So I wanted to ask you, what does it mean when people say the entanglement of gapped 1 + 1 dimensional QFT? So gap means there's a finite correlation length. So it's the saturation result I just showed you that this satisfies an area law. So what does this mean in 1 dimensions? Okay, so I give you two options. And I would like people that think it is the first option to write something on the chat, if there is anybody that thinks the first option. Okay, so nobody is writing anything, so they didn't fall for it. Perhaps it was a bit outrageous, this first option. I think I was a bit naughty to give you something that makes so little sense. But yeah, the first option doesn't make sense. So it doesn't depend on the area of the Riemann surface. But it means the second thing, it means that the entanglement grows at most with the area of the boundary regions. The thing is that, of course, in 1 dimension, there isn't really an area in the proper sense. What we have instead of an area is this number of boundary points. So because all of these things are constants, the only way entanglement can grow in this context, in a gap system, is by increasing this area, by increasing the number of boundary points. And in that sense, the entanglement satisfies an area law. Okay, so that's what it means in this context in 1 dimension. Okay, so let me show you a couple of results for the negativity as well, since we talked about it. So I'm going to start by showing you something that works in massive QFT. So this is the second situation, which is the one actually I've worked most on, I'm more familiar with. The correlation length is smaller than the length scales in the problem. So there is a result for that we got a few years ago. Actually, yeah, it's mentioned there. So these are actually a couple of results, both from a paper that we wrote some years ago. And so this is the logarithmic negativity of adjacent regions in a particular limit. So remember, what was adjacent regions? So in the logarithmic negativity, we usually had two regions A and B, and then we had a gap in the middle. So if we remove that gap, A and B are adjacent. So we have one length scale less in the problem. But in addition, if we take now one of these regions to be infinitely large, so actually this is this picture here on the left. So we have A and B that are adjacent, and now suppose I take B to be infinitely long as well. So the only finite length scale that is left in my problem is the length of A, of subsystem A. And in that very particular situation, it is possible to do a calculation in massive QFT and to find that this logarithmic negativity kind of saturates to some constant, a bit like the a bit like the entropy, with some, again, exponentially decaying corrections given by a Bessel function. Okay, so I appreciate that all these results are kind of a bit meaningless without explaining them. But as we advance with this course, we're going to see a calculation in detail of one of these results. So you'll see how these Bessel functions appear using techniques involving twist fields. So this will make a bit more sense later. But this is a result that is known. And there is also another result that is a bit similar, which is the logarithmic negativity, also in gaps theory, in another limit, which is the limit where instead the regions A and B are infinitely large and the region C is finite. So they are non-adjacent regions, but semi-infinite. So in this case, you also have only a length scale in the problem. And you can do a calculation using twist fields that will tell you that the leading contribution to the negativity is also of a very universal form. Okay, so for any quantum field theory in one dimension, is going to depend on the mass spectrum of the theory, just in this way. So capital N is the number of particles in the spectrum. So if you know a little bit about integral QFT, that would mean that if your theory was E8 total, let's say, you would have a sum up to 8 particles. But if your theory is the Icing field theory, you just have one mass scale, so you have one term in that sum. And the same for the one above. So there is remarkable universality in some sense, even when you go beyond criticality, which is something that I think less people are aware of, because criticality is by far in our area is more studied, I would say, and of more interest because, it, I guess, applies in more contexts. Okay, so these were the results I wanted to show you. So one last quiz, I think, for this set of notes. So another thing that you will read sometimes is that the entanglement entropy of CFT violates the area law in one dimension. So what does this mean? You have seen the formula. The entanglement entropy has a C over 3, or C times the number of boundary points over 6 times the log of length of the system. So why does it violate the area law? Because it grows faster than number of boundary points, or contains terms that do not depend on the number of boundary points. So if you think it's A, write something on the chat. So I think I have lost my audience, so you're thinking really hard. Anyone thinks it's A? No? One person. Thank you. Good. I'm not checking who it is, so don't be ashamed if you're not sure. I'm not looking at the name, so just look at the little number appearing on my chat, the number of votes. So, okay, timidly, a few votes are coming through for A. 6. Interesting. Okay, 7, 8, 9. Okay, so just a few. Yeah, relatively slow. Okay. So, okay, we can leave it there. So the rest of you are either thinking or you think it's B. So that means I was quite good at cooking up these answers, because B, yeah, it is A, actually. A is the correct answer. So it grows faster than number of boundary points. What does it mean faster? So I put in quotation marks because, I mean, faster in what variable? So it grows faster in the sense that it grows with the length of the region, right? So in gap systems, the entanglement of a large region doesn't grow with the length of the region, doesn't depend on the length, it's a trace of constant. And that constant is multiplied by the number of boundary points. And so the only way that constant might increase is by increasing the number of boundary points. In that sense, there is an area law. But in CFT, what we have is the number of boundary points, but we have log of length of the region. So the entropy grows logarithmically with the length of the region. And that logarithmic growth is what people say violates the area law. So in a sense, there is still an area law because there is the number of boundary points in front, but there is another dependence on the length, which makes the entropy grow not just with the number of boundary points, okay? So this is how this is meant, the violation of area law, okay? So I give you these questions just in case you go away and read things and you ask yourself, what do people mean when they say there is an area law or there is no area law? So this is the common way of seeing this. So I'm gonna end this set of slides, and I have another set coming a bit shorter, with an example, more practical, so a numerical example, just to give you an idea of where these things fit in if you are, for example, more familiar with quantum spin chains than QFT. So let's consider a very simple spin chain. This is the Icing spin chain. And this Icing spin chain depends on these two couplings, J and H. And you can carry out the scaling limit of this theory in two different ways. So if you set the field H equals 1 from the beginning, then this theory is critical. Okay, so its scaling limit is a conformal field theory with central charge a half. It's in effect a massless free fermion. Okay, so this is a critical model. On the other hand, if you take H to be a little bit bigger than 1, not very much, but a little, then what you have is a theory, the scaling limit is the Icing field theory, which is a theory that has a mass scale and effectively describes a Majorana free fermion with mass m, okay? So you get a theory which is, and of course, integrable. It's an integrable quantum field theory in one dimension. So this means that by tuning this H and taking the scaling limit, you can do numerics in this theory that will show you the different behaviors of entanglement I described to you. So let me show you a couple of pictures. So the picture on top, this is the entanglement entropy of an interval of length L. And I apologize because the legend and everything is very tiny. But it doesn't matter so much. So what the legend says is the value of H in each of these pictures. So if you look at the curve at the very top, this corresponds to H equals 1. This is the critical model. And in that critical model, what we expect is that the entanglement should grow logarithmically with L. And this is what we see. We see a log function. Not only that, but we see this log function very, very precisely. So we can do a fitting of this function there. And this fitting actually has a coefficient in front of the log, which is 0.5000003 divided by 3. So it's exactly central charge a half, as you would expect for free fermion. Okay, so this is a computation, okay, many people have done and a very long time ago. These pictures we did, okay, so we repeated this, but of course we didn't do it for the first time. But this 0.5, this we got, just doing some relatively simple numerics. And there is also a constant in there, which we also computed in our paper. That's why I cited there. So in general, numerics of this type were done very early in the story of entanglement, already in these two papers here, where people looked not just at Icing, but XXZ chain and other cases. Now, what about the other curves? So the other curves that you see underneath this one correspond to values of the field H, which are a little bit bigger than 1. So as I told you, when H is a little bit bigger than 1, this theory is not critical anymore. It's not described by CFT in the scaling limit. It's now a gapped theory. And the introduction of the gap is reflected by the fact that this function, this entropy, instead of growing and growing forever, what it does is saturate, which is what I told you should do. So when you make H not even that big, so the lowest curve here, the black one, is H 1.08, I think, or 06, you see that very quickly when L is above 8 or so, this function just becomes a constant. And the constant it flows to, of course, it depends on the correlation length, which depends on H. So it's a different one for each H. If H is very, very close to 1, this takes longer to happen, like in this green curve, but it will eventually saturate as well. Now, if you look at these curves here where you have saturation, okay, and you subtract the saturation constant. So you take, for example, this black curve here, this function, and you compute the saturation constant, which here is about 0.6 something, 66. You subtract that number and you look at what is left. What is left actually looks like the picture below. It's an exponentially decaying function. And if you do a fitting of this function, what you get very precisely is this minus 1/8 K0 of 2 ml. So this Bessel function I introduced earlier. So in this theory, because it's a free model and you can do exact diagonalization, you can really do these fittings very, very precisely. And you can see that these behaviors predicted by CFT and QFT, they are exactly matched by the numerics. Okay, so everything works as you would expect. It's all very nice. Okay, so this is the end of the first part of my presentation for this lecture. So this was the part about entanglement measures, main results for entanglement measures. So in the second part that I'm going to start now, I'm going to introduce the twist fields, okay? And we're going to talk about how you get these results I discussed now, but using twist fields instead. All right, so I'm going to get out of this screen just for a moment, because I have to open my other presentation. Okay, so it will take me just a second. Bear with me. And if you have—
Sorry, Olalla.
Yes?
I think we should make the break right now because it's—
Oh, you usually do
lecture at a break of 15 minutes, yes.
15?
Yes.
Oh, okay, I didn't know. Okay, that's fine with me. That's fine with me.
Okay, I think it's a natural place to make the break.
Yeah, no, it is. It's just I haven't attended the other one, so I didn't know how it's done. But I think that's a great idea. Okay.
Okay, so let's just break now and we meet at 3. We are here after the break. Please mute everyone, mute except Olalla, and let's start the second part of the lecture. Okay.
Okay, thanks. So, okay, so now I have introduced the main measures of entanglement to you. I have told you about some results, some more famous than others, about entanglement in one dimensions. So now I'm going to finally introduce this twist field, which a lot of my course is about. And so this is this lecture, Entanglement Measures as Correlators of Twist Fields. So the first thing I want to do is to tell you a little bit more generally what these twist fields are. So not just the one that features in entanglement, but twist fields in general, what they are. So whenever there is an internal symmetry in quantum field theory, there generally is a field associated with that symmetry. So this is a known result of quantum field theory that you're probably familiar with. And a well-known example, again, is this Icing model I already talked about. So let me tell you something about this first. So in conformal field theory, there is a minimal model, which is the Icing model. So it's the simplest minimal model. And usually we think of it in CFT as having 3 main primary fields: the identity, the energy field, and the spin field, sigma, sometimes called the order parameter. So this is the Icing model. Now, if you perturb this model and make it massive, you get the Icing field theory I already talked about. And both in the conformal and in the massive theory, there is also fermion in this theory, a Majorana fermion. Now, it turns out that this Majorana fermion is not local with respect to all these 3 fields that I mentioned. In fact, with respect to this fermion, the theory divides into 2 sectors. I think you probably have heard of the Ramon and the Schwarz sectors. So there is a C2 symmetry in this theory. And so there are fields that are local with respect to the fermion. And these are the energy again, the identity, and a field which is called mu, which is kind of the C2 counterpart of sigma. Even in the massive version, that is the case. And then there are fields that are semi-local or non-local, if you want, with respect to the fermion field. And actually, I cite Yurov Samologikov here, not because they discovered this, which they didn't, but because they talked about this in the context of the form factor program, which is going to feature quite a lot in my course. Okay, so what does this mean, being local or semi-local? Well, one way to think about this is to think about this spin field, this field sigma, as a field that sits in space-time at some point, as you see in this picture. And actually that point is associated with a branch, is a branch point, is the beginning of a branch cut associated to that field. And what that branch cut does is to implement this semi-locality. What it means is that if you think about the fermion going on a trip around this spin field, so if you exchange the spin field and the fermion, if you do this exchange in a certain order, the fermion will have to cross this branch cut. And when it crosses the branch cut, in this case, it picks up a minus sign, okay? And that's just because of this semi-locality property. Now, there is a more formal way to write. So this field sigma is a twist field. It's a field associated with the C2 symmetry. And it is also a field sitting at the origin of a branch cut. And branch point twist fields are going to be of the same type. It's just that the symmetry they're associated with is a more complicated one. There is a more formal way you can write this, which is through exchange relations. So if you now more generally think about the field phi, which could be the fermion again, or the fundamental field of your quantum field theory, and another field phi, unluckily I call them both phi and psi, sorry. So if you think about these two fields, phi and psi, what we are saying is that if one of them is a twist field, it turns out that when you exchange them, depending on the order of their position in space-time, if you exchange the two fields for a certain ordering, what you do is you pick up a factor, this omega. This omega was called by Yurov and Samologikov, I think they call it the semi-locality factor, which for the example of the Icing model is just a minus sign. And for this example of branch point twist field, is going to be something more complicated. So twist fields are non-local with respect to other fields in the quantum field theory, but they are still local in a wider sense, which is that they are local with respect to the Lagrangian density of the theory, because they respect the internal symmetry. So we're talking about an internal symmetry of the theory. And this is why it is important in the context of entanglement to have a replica theory, because having a replica theory means that the theory has symmetry and the cyclic permutation of copies, which is exactly the symmetry to which this branch point twist field would be associated with. So this is a brief introduction to twist fields, very brief. Now I want to ask you something. I think probably there will be many of you that are more familiar with spin chains than QFT again. So I would like you to think just very quickly, if you can, because we don't have a lot of time, about whether or not you could think about twist fields in a spin chain setting as well. For example, in the context of the Ising spin chain. So can you have an understanding of this example of the spin field in the context of the chain? Okay, and I give you two options. No, you can only think of twist fields in QFT, or you can also think of twist fields in the chain. So if you think it is A, I would like you to answer as quickly as you can, because we cannot spend as much time this time. Okay, so it seems to take a little bit more time, perhaps because it's a slightly more difficult question. They get a bit more difficult as we go. Anyone will make a move for A? So perhaps you think that it is B. So there is one, I think there is one vote for A. They only make sense in quantum field theory. So actually the correct answer is B. Okay, so I think if you didn't vote for that reason, then you are in the majority. So twist fields are related to local operators on the chain. So there is a way in which you can link this notion of twist field to quantum spin chains. And in the Icing model, actually the picture is not so hard to understand. So probably many of you would be familiar with the Jordan-Wigner transformation in the Icing model, which relates the spin operators to the fermionic operators. And you probably remember that the relation between, for example, sigma plus minus and the fermions is a relation that is non-local, in the sense that these spin fields, they are exponentials of a sum over products of lots of these fermions. So, so this non-locality, the fact that lots of fermions sitting at different sides of the chain are involved, what it means is that when you do the scaling limit of these operators, this big sum of fermionic operators becomes an infinite sum, becomes an extended object. And that extended object gives rise to this branch cut I was talking about, okay? So there's a direct link between a spin chain description and a quantum field theory description. So twist fields are related to non-local operators in the chain, or not very tightly localized, at least. So this is, okay, a very superficial answer, but just to give you an idea that this can be done. I have another question that I think one has to ask in this course, because it's about branch point twist fields. So perhaps this one is one where you will have different opinions, and I think it's an interesting one to discuss. So when were branch point twist fields discovered? Or, well, discovered in quotation marks, because it's not like a continent, but where did they first appear? So I'm going to give you three common options. Sorry, the A is in the wrong place, so it should be there. So A would be the famous paper of Pasquale and John. B would be they've been known forever. And C would be that they come from our paper in 2008. So if you think it's A, I would like you to vote now for A. And don't be shy. I know that Pasquale and I are here, but we're not going to take it personal, whatever you answer, I'm sure. Oi, okay. Have some votes. One vote so far. Okay, keep them coming. Is that all for A? Okay, so who thinks, okay, we stop the A. So who thinks it's B? They have been known for ages. Could you vote? Okay, so quite a few people are voting B, which is interesting. Okay, lots of people going for B. Quite a few, okay, I'm not counting, but yeah, at least 15. Okay, and some more. Okay, and let's assume the rest think is C, which would be the majority in this case. So perhaps you're trying to be nice to me because I'm giving the course, so that's nice of you. Okay, so that is interesting. So I'm asking this because actually, in a certain sense, depending on how you think about the question, the three answers are correct. So it depends what you mean by discovering the branch point twist field. So how do you take the question? So this is what I want to come to in my next slide. So the definition. So I would say that the most kind of correct answer is actually B. They have been known for quite a while, but not all of us were aware of this. So in a sense, I think in the context of entanglement, we kind of, they were sort of rediscovered again. So we can say that they have been known for a while, that there is a special field that appears when you study conformal field theory in an orbifold. So you study conformal field theory in effect almost in a replica theory, like the one I was talking about. And it turns out that in the 80s and 90s, orbifold CFT was all the rage. There were lots of papers about this. And if you look at some of these papers, you will actually find people talking about a field with a conformal dimension like this, what I call the branch point twist field. So this is one sense in which this has been known for ages. So for quite a while, before some of you were born, I'm sure. Now, what people found in those papers is that in such theories, there would be naturally a primary field with a dimension like the one you see here on the left, which is the usual dimension we attribute to this branch point twist field. Here, I give another dimension of another field, which is also a branch point twist field of a slightly different kind, is what I call a composite twist field. And this is a twist field you will have in conformal field theories that are non-unitary. So if the theory is non-unitary, the central charge in some cases is negative, but there is another number that is positive. It's called the effective central charge. And I'll perhaps talk about this a little bit later in this lesson. So it's not so important. But in those theories, you would have some other twist field definition, which will have this dimension. And this also actually can be found in these old papers. So this is one possible answer. Now, in the context of entanglement, the first people, as far as I know, that thought about entanglement as something you could express in terms of correlation functions of a field, these were Calabrese and Cardy. So they thought about this in the context of entanglement, and in their very famous paper, they computed the dimension of the field you would need to do a calculation of entanglement, and they found this dimension to be the same as here divided by n. So they have a slight difference of a factor n. So that's why I don't call it T, because it's a slightly different field. Now, the way they thought about this field, and of course Pasquale is here, he can correct me if I'm saying something wrong, but the way I understand their paper is that they define this field as a field in conformal field theory, which is associated to a conical singularity in the complex plane, which are exactly these branch points that we had in the famous manifold I showed you in the first part of this lecture. So we have a field associated to conical singularities in conformal field theory. They computed the dimension and they wrote entanglement in terms of correlators of this field. So this is one point of view. What we did later on in our paper, so we also did something. So one thing we did is that we call these fields branch point twist fields. So this is something that we did. We gave them this name. Actually, I think it was Benjamin's idea, my collaborator. And we introduced this notation for the twist field and the anti-twist field, the T tilde. And what we did in our paper really was to describe these fields as symmetry fields. So this idea that there's a branch cut associated to the field, and that's when other fields go around, they might pick up a face or something might happen to them. This is something that we discussed in this paper for the first time. And this is the picture that allowed us to then generalize these fields to the massive situation, okay, when you go beyond conformal field theory. So that, in summary, that means that depending on your point of view, in a sense, all three answers are correct. So different people have thought about these fields in the context of CFT and in the context of entanglement. So let me say then a bit more about this. So, well, actually this composite twist field, we found it when we looked at entanglement in non-unitary CFT. So this is a little bit esoteric for this course, but this is something that we studied quite a bit later. And then we came across these other fields. So what else can we say? So in terms of this branch of these twist fields that I just introduced, this T and this T tilde, I'm going to call it T dagger in the future, just to make clear it's the conjugate. What we can say, so I'm going to give you sort of a memory rule for entanglement. So the connection between entanglement and twist fields, without justifying it very much, just to say that if you want to compute the entanglement entropy of multiple disconnected regions, so you have a system like this, and your region A is the union of all these A1, A2, A3, A4, and the region B is the black bit, so the rest, so the complement of A, then it turns out, as a general statement, you can say that the Renyi entropy of these K disconnected regions in one-dimensional QFT, so that could be CFT or massive QFT, in a replica state, so in some state, pure state phi, and you have n copies of the system, in terms of twist fields, and this is going to be essentially the 2K point function of those fields with essentially for each of these intervals, let's say A1, you're going to be essentially inserting a twist field at each boundary point of those intervals. And in the case of the entanglement entropy, you insert a field T on the leftmost boundary point and a conjugate twist field, so T dagger, on the rightmost boundary point. And you do that for each of these little regions, say 1, A2, and so on. So you end up with this 2K point function you have to compute for these fields on the replica theory. And this epsilon, again, is something I like to write always. So this is this non-universal constant that you can write there, because there is always a non-universal constant you can add. And the log is from the definition of entropy. So as you can see, if you remember my definition of Renyi entropies, this correlation function essentially is the trace of rho to the n. Okay, so this is the replica partition function. So this is what you have. So it's pretty simple. I mean, if you accept this, any entanglement entropy you want to compute, well, you have as many fields as boundary points. That's it. So the more boundary points, the more complicated the calculation. If you're computing the negativity instead, then it's actually pretty simple in terms of twist fields. Let's look just at the two regions A, B, as before. You have 4 boundary points, so you're going to have 4 twist fields. But because in the region B, you have this funny partial transposition, the replica version of this logarithmic negativity is going to be a 4-point function of T dagger, T. So the second pair of fields is exchanged, okay? And again, this is on a replica theory on a pure state phi in this definition, okay? So that means that if you want to use twist fields, now suddenly you can think of entanglement measures as correlation functions. Now, this idea is very powerful, especially when you go beyond criticality. Just because at criticality, sometimes, well, you can use conformal maps and other techniques to compute things. But when you're not at criticality, those techniques are not available anymore. And on the other hand, there are many techniques to compute correlation functions. And that's why these twist fields are so useful to get results in massive theories beyond criticality. So if we take these definitions, I have a little poll. So I just want to ask you something about these correlation functions before I go on. So how is this useful? Well, in a way, I already told you. So there are many techniques in QFT to compute correlation functions, but do we have to compute these correlation functions on that n-sheeted manifold, that complicated manifold, or is there some simplification? Okay, so I give you two difficult options. So one is that it's useful, but somehow we have to use some method to map to R2 or to the complex plane. Or these are now correlation functions already on the complex plane on R2, so they can be computed by standard methods. And that's really the point of twist fields. So does anyone think A is the correct answer? Just quickly, if you can. Okay, I don't see any answers coming for A. So perhaps that means that you all think it's B. Okay, I'm going to assume that's the case because that's the correct answer. So, so you see that what is powerful about twist fields is that essentially they get rid of the manifold, or not quite. Instead of getting, I mean, they get rid of, it's a little bit like when you have multi-valued complex functions and you want to make them single valued, and you have two ways to do that. Either you define them on a Riemann surface, or you introduce a branch cut and branch points. So introduce a branch cut and kind of connection conditions in this branch cut. Well, the twist fields kind of do this second thing for you. So when you have twist fields, these correlation functions I was showing you, these are correlation functions on the complex plane. And how do you get rid of the Riemann surface structure? Well, you get rid of that thanks to the non-trivial exchange relations these fields have with other fields. So they implement essentially the action of this branch cut in there for you. And that is really the big advantage of this. So now you can use the standard methods. That's really the point of having these twist fields, especially beyond criticality. So let me show you how you get the usual results in this way. So the results I show you for the entanglement entropy, and in fact, many of these results I'm going to show you here, they are given to you as an exercise for you to do in the Excel sheet that you can find on the website. So if you want to try and do these little calculations, do have a look later. So I'm not going to explain too much. I'll let you try and do them, but they're very simple. So obviously the entropy of an interval in this context becomes related to a two-point function. And if you're in CFT, a two-point function is a very simple object. So very quickly, just using the definition, you get your Renyi entropy result. So logarithmic growth follows from parallel scaling of two-point functions in CFT in this point of view. Now, what about saturation in quantum field theory, massive quantum field theory? That was also one of the nice results we saw earlier. Well, saturation follows instead from a very fundamental property of QFT, which is that if you have a two-point function like this one, in a massive theory, so in a gap theory with a finite correlation length, and you take these two fields very far from each other, so you make this length very large, well, you have something called clustering of correlators. So essentially, at some point, these fields do not see each other anymore, and the correlation function clusters into a product of one-point functions. Now, the one-point function of T and its conjugate is the same, so you get one-point function squared. And one-point functions in QFT, these are constants, essentially. Well, they scale with the mass scale of the theory or the correlation length, if you wish. So if you just use the scaling laws of one-point functions, which are dictated by QFT. So in general, one-point function of twist field scales like this, where delta T is the conformal dimension of the conformal version of this field, and A is a constant. Then with these definitions, you immediately get this saturation constant I presented earlier. The exponentially decaying corrections we talked about, well, we're going to discuss those later in my last lecture. We're going to explain how they come about, but these are essentially the next correction to this clustering that I'm showing you here. So there are more terms that depend on the length of the region, and the first relevant one for the von Neumann entropy are these Bessel function corrections. What other things can we do? So actually, I think I'm going to jump this because we are running a bit out of time. So let me do this other poll instead, because this is relevant for the next thing I want to present. So if you are familiar with conformal field theory, and I think probably many of you are, think about the twist field in conformal field theory and think about the operator product expansion of two of these twist fields, T with itself, not its conjugate, but itself. So if you do this OPE, what would you get? What would be the leading contribution to this OPE, the leading field? Would it be the identity? Would it be the same branch point twist field or a possibly different branch point twist field? What did you think? If you think it's A, I'd like you to try something quickly. Okay, so I assume nobody thinks it's A. Does anybody think it's B? Also no, and that's it. Oh, there is a one for B, I think. Let me see. Somebody has voted for C. Okay, Jerome has said a C. Thank you very much. Anybody else thinks anything? B or C? Or you just don't know? Okay, maybe that is a don't know. Okay, I got a point. Got another answer here. 2 people have answered C. Okay, I got 2 C's. Okay. So C is actually the correct answer. I mean, B is correct sometimes in a certain sense. A is definitely not correct. And A cannot be correct because when you do the OP of these fields, the twist property has to be preserved. And this is a field associated to cyclic permutation symmetry. So if you apply 2 of them together, you cannot get a field that's neutral. So this cannot happen. What has to happen is that you get another twist field of some kind. And this other twist field plays a role actually when you do computations of the negativity, the logarithmic negativity. So that's why I was asking you this here. So let me show you some formulas for the negativity. So remember when we talked about adjacent regions in the negativity. So the negativity formula I showed you earlier had a 4-point function in general. So it was T, T dagger, T dagger, T. But if the regions A and B are adjoint, that means that there are 2 of the boundary points that coincide of these regions. So the kind of rightmost boundary point of region A coincides with the leftmost boundary point of region B. And what this means in terms of twist fields is that there's kind of a collision of twist fields. And when these fields collide, the 2 T daggers collide, what you get is a new twist field, which actually Pasquale and collaborators called the field T squared. So it's a new twist field. Let's call it T squared. And what you get in CFT is a 3-point function to compute in that case. And in CFT, 3-point functions are very highly constrained. So actually you can do this calculation and you can get this replica version of the logarithmic negativity. And this is not a hard calculation, but this is a problem I'm going to leave for you to try and do. It's on the exercise sheet. Okay, so so you get again some logarithmic growth with the length, and again comes from the power law scaling of 3-point functions in CFT. Okay, in this context. Now, what is this T squared T dagger square? So again, this is a question that's on the exercise sheet, but there is a very beautiful explanation that was proposed in this paper, which is the idea that if you bring these 2 fields together, well, you get a new twist field that essentially, instead of kind of moving you from one copy, from one sheet of the Riemann surface to the next one, it moves you to 2 above. So it kind of jumps by 2, okay? And I actually still have to show you the exchange relations for twist fields, I think, a little bit later. So this is a bit early to explain. So this is a twist field that essentially connects sheets that are 2 places away. And actually this field behaves very differently whether n is even or odd. It has different properties. For the negativity, remember we need n even mainly. So that's in that case, actually this field factorizes into a product of 2 standard fields for half the number of sheets. So kind of you have the even labeled and the odd labeled sheets somehow, and you have a twist field associated to these 2 kind of Riemann surfaces. So this is something that I'll come back to a little bit later, so don't worry if you don't understand it completely now. But there is an exercise as well for you to try about this. And if you look at the negativity of adjacent regions in the massive case, so well, when you have correlation length that is much smaller than the length of the system, what you get instead is some sort of saturation. And that follows from the same property of clustering I mentioned earlier. So from the fact that when you have a mass scale, you can factorize all these fields. Okay, so that's what I'm writing there. So I'm almost at the end, so don't worry, I think I'm going to finish more or less on time for the discussion. There's 1 minute left. So just to mention that if you want more generally to compute the entropy of two disconnected regions or the logarithmic negativity of two disconnected regions, well, you need to compute some 4-point functions such as this. Okay, and even in conformal field theory, these 4-point functions are not so easy to compute. They are highly constrained, but they are not fully constrained. So there is always one part that depends on the specific theory you're looking at. And well, I have also an exercise on the Excel sheet for you to try and do the case of the free fermion here. So I think that's almost everything. I think I have, well, analytic continuation to N1 is very complicated here, so we're not going to enter into this. I have one final question for you just to end this session. So, okay, so we have defined this twist field. I haven't gone into lots of these details. I just told you that entanglement measures are correlators of this field. I'm going to tell you a little bit more about it in the next lecture. But given that this field is symmetry field associated to cyclic permutation symmetry, what do you think happens to this field when you put n equals 1? So n is the replica number. So you have one copy of the system. So what should happen to twist field in this case? Does it have a good definition? So is it not well defined? Is it just the identity, or is it something complicated that we don't really want to go into? What do you think? Does anyone think is answer A? Okay, nobody's going for A. Does anyone think it's answer B? It becomes identity. Anyone for that? Okay, 1, 2, 3, 4. Okay, very good. So lots of people going for B. Okay, lots, but I mean, still a few missing, but okay, quite a few. Okay, nice, thank you. Okay, so your instinct is correct there. So the B is correct. Yeah, it becomes the identity, and that's what should happen, right? So when n goes to 1, if the field is associated to cyclic permutation of copies and there are no longer any copies, then it would be natural that this field becomes identity, and that's what it does. And this is an important property we will see later on. So when we study something called the form factors, the matrix elements of this field, we will see that actually when n is equal to 1, these form factors have to be 0. And this is quite a strong constraint that we can use actually to our advantage. So I think for today, this is enough. And I think we're just on time. So this is good. I hope you got something out of this, that you enjoyed it. Have a look at the exercises if you want. And I'm going to see you tomorrow again, and now for the discussion as well.
Thank you, Olalla. So I think we should start if there are questions by anyone that wants to. I see this clapping. I don't see. You can either raise your hand or just ask to talk, as you prefer.
Yeah, whatever you like. If you have any questions, I guess about my talk would make sense. But I guess this is the discussion session both for me and Balázs. So questions for either of us.